Hi, students. In this video, I want to go over factoring polynomials because it's a lot of it is using certain techniques to help you factor that maybe aren't always intuitive, but once you get the hang of it, it'll come to you pretty naturally after a lot of practice, of course, just like anything. So I have, how many examples do I have for us today? I have 5 examples. They kind of get harder as we go. We're going to work from binomials, trinomials, and polynomials with 4 terms. Okay, so let me get started with our first example. Is going to be the only binomial that we have. Binomials really, besides looking for the GCF, the greatest common factor between your 2 terms, there's really only a couple of tricks for binomials. So we are going to do one that is what we call a difference of squares. So in our first example, what we're going to try to factor is 2x squared minus 98. And keep in mind here, we are just factoring this isn't an equation, so we can't solve for the variable, okay? A lot of times something like this will be inside of an equation and we will need to factor it in order to solve. But in this case, we're just practicing factoring, okay? So the first thing you want to look for when you try to factor anything is always a GCF. It's going to make it tremendously easier if you can factor off any common factors from every single term. Here we have 2 terms. They both have even coefficients, so we've got a factor of 2 that we can pull off of these guys. So this expression can be rewritten as 2 times x squared minus 49. All right. And then once we pull that factor of 2 off, we want to look at this x squared minus 49 and ask ourselves, is this a difference of squares or a difference of cubes or a sum of cubes? And in this case, we just have an x squared minus 49. These are both perfect squares. All right, so since these are both perfect squares and there's a subtraction sign in between them, we've got a difference of squares. Keep in mind, if you have a plus sign in between 2 perfect squares, you cannot factor that because a sum of squares is actually prime. Okay, so when you have binomials, there's only 3 situations where you can factor, with the exception of factoring a GCF: the difference of squares, and then the sum or the difference of cubes. Okay, in this case, we've got our difference of squares, so we've got our 2 here, and this is going to factor to x plus 7 times x minus 7. Okay, so now this thing is fully factored. It has 3 prime factors: 2, x plus 7, and x minus 7. All right, so that's factoring a binomial. Right. Let's move on to the next example, which is going to be a simple trinomial, which is a quadratic that has a leading coefficient of 1. So this is a trinomial or a quadratic with a leading coefficient of 1. So these are the easier type to factor if they are factorable. Now, it is possible for these to not factor to real solutions, or for their factors to be just not whole numbers. And in that case, you can use the quadratic formula. Plug these guys into the quadratic formula, and then you'll see if it has real solutions or not. Okay. For this example, it does. So here we're going to use the technique where we want to find two numbers. They are going to add to this middle coefficient, and they're going to multiply to our constant term, okay? Those two numbers that add to -10 and multiply to +24, first of all, just looking at the signs, we know they both need to be negative. If they're gonna multiply to a positive number, then they both have to have the same sign. And if they're going to add to a negative number, then they must both be negative numbers. Okay. So in this case, those numbers are going to be -6 and -4. Okay. And so that guy's completely factored into these two factors, x minus 6 and x minus 4. If you're wondering how that technique works out, if you're wondering how can we go backwards like this, right? Why are we adding to this middle term and multiplying to this last term? If you're wondering how that works, well, you just go forward and see that we're just working in reverse. So if I were to distribute this x to both terms here, and then this 6 to both terms here, I would get something that looks like this: x squared minus 4x, right? That's the first x times both of these terms. And then when I go to multiply the -6 times x, I get -6x, and then -6 times the -4, we multiply -6 times -4, and that gives us the +24, okay? So that's why we look for those two numbers that are going to add to our -10, right? And they're going to multiply to our +24, okay? So that's the logic of that one. If you want to sometimes just multiply it out after you've finished doing the factoring to confirm that it really does get you back to our original trinomial, you can do that. So let's do another trinomial, but this time with a leading coefficient that is not 1. So here we have, again, another trinomial, but our leading coefficient isn't 1, so we can't use the same technique. The first thing you want to check for these guys is there a GCF that I can factor off? If there's a GCF, sometimes once you factor that to the outside, you might find that you do have a leading coefficient of 1, and it's a lot easier to factor. In this case, there is no GCF. 7 is prime. So we are going to have to use another technique, which is called factoring by grouping. And basically here, what we're doing is it's sort of using the same logic as before. People found this out by working backwards. What we need to do is split our middle term into two pieces. And we want those two pieces to actually share factors. We want one of these pieces to share factors with the 20, and we want the other piece to share factors with this guy in a way that after we factor those two pairs, they'll have a common factor between the two pairs, okay? So the trick here is we need to factor that 7x into two numbers. They're going to have to add up to 7x, but we want them to also multiply to the same thing as our leading coefficient and our constant term. So we need to add to 7, and we need to multiply to whatever 6 times -20 is, which happens to be -120. Okay, So they're going to add to 7. They're going to multiply to negative 120. So clearly our two numbers are going to be a negative number and a positive number, right? A negative and a positive will multiply to that negative 120, and a negative and a positive, if they differ just by 7, then when they add together, we'll just get that 7, okay? If you're wondering how you would even begin to figure out what those two numbers are, I'm going to tell you, you want to start by looking at all the numbers that multiply to negative 120. And really, you can kind of just ignore that negative sign and look for numbers that multiply to 120. And when you get two numbers that multiply to 120, but differ by just 7, then you've found your two numbers, okay? If you want, you can start by listing, okay, we've got 1 times 120. We've got 2 times 60. And you would kind of keep going and going until you realize that we've got 8 times 15 multiplied to 120. But I look at 8 times 15 and I realize those only differ by 7. So if I make that a -8, -8 times positive 15 multiplies to 120, adds up to 7. So those are my numbers there. Start by looking at the step that multiplies, because there's only a finite list of things that are going to multiply to your number, but there's infinite things that are going to add to 7 when you can do positive and negative numbers, okay? So all we do now that we know our two numbers are -8 and 15 is we replace our 7x with a -8x and a 15x. So we'll still have our 6x squared minus 8x plus 15x and our minus 20. So see what we did here in green? We are allowed to do this because we replaced our 7x with two terms that are equivalent to 7x, okay? That's kind of like we did with our fractions, where we made equivalent fractions. So -8x plus 15x is equal to 7x. That's why we're allowed to do this. And just so you know, it doesn't matter which term you put first. The way the factoring works out, it will work out either way, okay? So now we are just going to look at our first two terms and factor those guys, and then look at our second two terms and factor those guys. Okay, 6x squared and -8x both share a factor of 2x. So we can factor 2x out. And we're left with 3x minus 4. Okay. And then over here, our 15x and our -20 both share a factor of 5. So we can factor that 5 out, and we're left with a 3x and a -4. See how that works? Because we very, very carefully picked these two numbers to replace our 7x with, because we very carefully picked them. When we factor later, we end up with these similar factors, this 3x minus 4 and this 3x minus 4. So now what we are looking at is we actually only have two terms here. This is one term, and it has a factor of 3x minus 4, and this is another term, and it has a factor of 3x minus 4. So now we're just going to factor these two terms. Let's pull their common factor out. That 3x minus 4 is common to both of those terms, which I've underlined in yellow. And then what's left is a 2x and a plus 5. Right. So we pulled this common factor of 3x minus 4 out of our two terms there. Okay. And that is our final answer. We have factored that polynomial. Okay. So that's factoring by grouping. It takes a little work just to figure out these two guys that are going to add to our 7, multiply to our 120. Remember, this 120 came from multiplying these two coefficients. Okay. If you want to pause there and go over what we did again, I would recommend that. But moving on, let's take a look at our next example. Our next example is going to be a polynomial with 4 terms. All right. So this has 4 terms. As you see, it can't be simplified anymore. When you have more than 3 terms and they can't be simplified, really what you are looking for is you can only you can factor out a GCF, and then after that you can factor by grouping. But because these are not 4 terms that we have specifically engineered to factor by grouping like we did in the previous example, it's very possible that polynomials with 4 terms will not factor by grouping. You can group the but those 2 terms then might not have common factors, and then you just can't factor them. But it does look like there are some patterns here, 2s and 3s, 2s and 3s. So sometimes in special cases, you can factor these by grouping into 2 binomials. Okay, so let's just try. Let's take our first 2 terms and our second 2 terms. And keep in mind, in something like this, when you're factoring by grouping, you can feel free to move your terms around into ways that you think they might factor better. Okay. So when I look at my first 2 terms, they both have a factor of x squared. So I'm going to pull an x squared out of just my first 2 terms. The very first term is still left with a 2 and an x. And that second term, that 3x squared, is just left with a 3. Okay. Now, when I look at my second 2 terms, they actually don't have any common factors, except that they are both negative. And if I want, I can factor out a -1. So if I factor out that -1, then we are left with a positive 2x and a positive 3. All right. And in this case, we got lucky. These were some nice numbers that actually factor by grouping pretty well. Now we're in the same situation we saw in the previous example, right? Essentially, we've got 2 terms here, this guy, and then this guy is being subtracted from it. They both have a common factor of that 2x plus 3. So we can pull that 2x plus 3 is in both terms. So we can pull that 2x plus 3. We can factor that out to the outside. And we've got 2x plus 3. What's left is an x squared minus 1. All right. So this guy here factors nicely. You can see, though, we kind of got lucky with the 2, 3, -2, -3. Okay. All right. Let's move on to one more example that is quite tricky. And we'll see how far we get with it. Okay, so here we've got a trinomial, but it is not necessarily a quadratic. Okay. There are a couple things we can do, though, to make it behave like a quadratic, and so we can factor it like 1. The first thing that we could do, and I think maybe the most straightforward, is that we can treat the y as if it is part of the constant term. And then what we're left with is, we see this, we've got this, our first term's a term, our second term is an x term, and then our third term is a constant term. So we can factor this like we would factor a quadratic, and we're going to treat the x neutral variable and the y we're going to include as part of our constant term. Okay. But the very first thing that we always want to do is look for a GCF to see if we can factor it off. All of these terms have even coefficients, so we've got a 2 that we can factor off, and then all of these have 2 factors of y that we can also pull off, and that'll just help bring the exponents on those y's down and make them look a little cleaner. So we're going to factor out a 2y squared, and we're going to be left with a 4x squared minus 24yx plus a 9y squared. And if you're wondering why I moved the y in front of the x here, it's because, like I said, we are going to pretend that this y is part of the coefficient. Actually, now that we've done this factoring, we could go either direction. We could pretend like we are a quadratic in terms of y and the x is part of the coefficients, or we could pretend that we are a quadratic in terms of x and the y is part of the coefficient. Because both of them have, both our x squared term and our y squared term have leading coefficients that are not 1, it really, either way we go, we're still going to have to do that more difficult factoring by grouping. Okay. So if we want to factor by grouping, okay, so before I talk about factoring by grouping, one thing you might notice here is that what we are left with is actually a perfect square. Okay, so this first term is 2 squared, or sorry, 2x squared. And this last term is 3y squared. So this is actually going to factor into a binomial squared, or the 2 binomial factors of this are the same. Okay, if you see that now, you can go ahead and do that factoring, but sometimes it's hard to see that. So I'm going to do just our factoring by grouping like we did before. And then you might understand what I mean when you see the answer, how I'm saying that's perfect square. So factoring by grouping says we need to break up this term here, this negative 24yx. And remember, we're just going to look at its coefficients. We need to break that term into 2 pieces. They have to add up to this negative 24yx, and they need to multiply, or the coefficient needs to multiply to 4 times 9y squared. And keep in mind, guys, that the x's we're treating as our variables, but the y's we're treating as coefficients. Okay. So that's why we need to multiply to a 36y squared, because that's 4 times 9y squared. And we want to add to a negative 24y, because that's the coefficient on our x term. Okay. So how can we do that? Well, that's going to be a negative 6y, right? Negative 6y times negative 6y is a positive 36y squared. But it adds to that negative 12y, and I'm really sorry, guys, this is supposed to be a negative 12. Negative 12y. So we wanted to multiply to 36y squared, add to a negative 12y. And so that's going to be negative 6y times negative 6y. So that's how we're going to break up our centerpiece. This guy's going to become a negative 6yx, negative 6yx, plus 9y squared. All right. All we did was break up this centerpiece into two different terms that add back up to that original term, but their coefficients multiply to the same thing that the coefficients of our first and last term multiply to. Okay, so now we can factor our first two terms. These guys here are going to factor to, let's see, we've got a constant term, a similar factor of 2x. So we can pull a 2x out. And we are going to be left with another 2x inside and a minus 3y. So that's those first two terms. And then our second two terms are going to factor to, I like to put a plus there, unless we're factoring out a negative from both terms. So our second two terms, these guys here, they both have a 3y. So we're going to pull out a 3y. And then left inside is going to be a negative 2x. And, oops, sorry, let me put them in black. A negative 2x and a positive 3y. And you see, we've got a little discrepancy here in our signs. This is a positive 2x minus 3y. This is a negative 2x plus 3y. So indeed, I should factor a negative 1 out. And I will just factor a negative 1 out by changing this sign here. And then I can change both the signs inside. That's a negative 3. Then we end up with a positive 2y and or positive 2x and a negative 3y. Okay. And that is all inside those larger brackets. Now we can finally factor that common factor of the 2x minus 3y. That's the factor in yellow. We can factor that off of our two terms. But our two terms, notice what's going to remain is a 2x minus 3y when I factor off the common term of 2x minus 3y. Okay. So we've still got this 2y squared on the outside. And then we've got a 2x minus 3y that we are factoring out as the common term between our two inside terms. And then what is left remaining, as I've underlined in green, is a 2x minus 3y. Okay. Now, we could say that we are done, or we could notice that we have two terms, the one in green and the one in yellow, that are both a 2x minus 3y. And so if we really wanted to, we could rewrite this as 2y. Sorry, let me write it in red. This whole thing could be 2y squared times 2x minus 3y. And instead of writing that factor twice, I could write it as squared. All right, so that is our final factorization of that trinomial from the very beginning. Hopefully I did not confuse you guys when I wrote the 24 here. I'm very sorry about how I factored that. Hopefully that got all cleared up. Maybe try working through that one on your own. To see if you can get the same thing. So that's factoring polynomials. And if you guys can master all that stuff, it will help you a lot going forward. Take a look at some of the examples in the factoring document, Canvas shell. and try to work through them. Ask me if you have any questions. Certainly, if you have some factoring problems that you're having trouble with, post them on the discussion board as well.